Okay, hi everyone. Let us start with today's exercise class. So my plan for the exercise class today is to look at the topics of the two exercises which appear in this week's exercise sheet. Yeah, so I initially put up the exercise sheet on Tuesday, but today morning I substituted it with some minor corrections about the sign in one of the exercises. So if you already downloaded it, please re-download it because there is a change in one sign. Okay, so the first exercise is about coupling a certain observable that we cannot really access directly to the momentum of the particle. And in the lecture, you've seen how to couple such an observable to the position. And here we'll just repeat the whole process, but for coupling it to the momentum. So the idea here is that we have a certain observable, which is not directly accessible to us, but we still want to measure it. And the idea of how we measure it is we just couple it to another observable, which in this case is the momentum of the particle. So we couple it to the momentum. And then by coupling, we can just then measure the momentum of the particle, and that will consequently lead to the measuring of the observable itself, which otherwise would not be directly accessible. Yeah, and I guess like the classical intuition for this could also be that, for example, if you're trying to see in the dark, then you your eyes, your ocular apparatus doesn't have enough precision and power to see in the dark. However, if you wear infrared glasses, then you could see, so you could see something. So essentially it just like it can be seen as you coupling to this device, which allows you to distinguish things in the dark. Okay, so the setup is we have a Hilbert space which corresponds to the system of interest, which we want to measure. And the hx, which corresponds to the Hilbert space of the particle, like in coordinates or momentum basis. Okay, and then we start with the following initial state. Ax, psi 0 tilde ax, which is a tensor product of states on system A and of the particle x. By psi 0 on x. And this is psi 0 of x. We can just write it as, in terms of position basis, for example, as an integral. And the proposition for the coupling Hamiltonian, which would achieve the coupling between the observable A, the system of interest A, and the momentum of the particle, is the following. So the Hamiltonian H, which is the interaction Hamiltonian, would be the observable MA that we're trying to measure on system A, and the tensor product with the X operator acting on the particle. And the observable MA on the system A, we just write it as sum over I, AI, IIA. Okay, so the first thing that we have, and now let us carry on with the derivation and see why does this Hamiltonian indeed achieve the coupling between the system A and the momentum of the particle. So for this, first we have to so this coupling is achieved by evolving under this interaction Hamiltonian here for a certain time t. And so first we need to write out how exactly this evolution would look like. So what is the unitary u of t, which corresponds to the system evolving under this interaction Hamiltonian for the time t. So as we have seen before, like from the Schrödinger's equation, the evolution operator under the Hamiltonian t for the under the Hamiltonian h for the time t looks like this. So it's e to the power minus it over h bar h. So now we just substitute h with what we have here, ma tensor product xx. And now we do what we already done a lot of times. We just expand to see how these exponential operator exponential acts. We just write it out in terms of the series. So we have as sum over n, 1 over n factorial minus it over h bar to the power n, ma tensor products xx to the power n. Since this is a tensor product, which and the operators in the tensor product act on a different Hilbert spaces, then we can just write this out as ma to the power n tensor product xx to the power n. Now to understand, now let us continue with the with the derivation of u of t. But first, sorry. But first, let us see what is exactly this observable ma to the power n, which appears in this operator here. So let us first look at how ma squared looks like. So ma squared is just ma by ma. So we write the first ma and the second ma is the next on a. And we arrive here to the sum over ij, aj, ai, j, j, I. And the bracket here, it gives us delta ij, the Kronecker delta ij, which is because the bases that we're looking at are orthonormal. And hence, the only terms that survive in this sum are those for which I is equal to j. So essentially what we get is this would be sum over I, ai squared, I. Okay, and quite trivially, you can see, also you can prove it formally by induction, that then ma to the power n would just be sum over I, ai to the power n, I acting on a. Okay, so then we can finally write out that our u of t which we had here below, we can write it out as sum over n, 1 over n factorial, minus it over h to the power n. Then here it's sum over ai to the power n iia, tensor product xx. Let's make sure this is separated. Okay, and now let us evolve the initial state under this unitary evolution. So now we apply our unitary evolution to the initial state psi 0 tilde ax. So this would be just applying u of t to the state sum over j, cj, jj, a, tensor product psi 0 x. Okay, now let us substitute u of t. Let's substitute u of t with what we found out above. So what we get is sum over n, 1 over n factorial, minus t it over h to the power n, sum over I, ain, ii, so cj comes here from the state, and here we have jj, tensor product, and the x just acts on psi 0. Okay, now let us massage this equation. So what we get here, so this x, I did a mistake here. So this has to be x to the power n. So here is also to the power n because it's in the series. Okay, so here we do the same as we did above. So ij bracket ij is just delta ij. And what we end up with is sum over n, 1 over n factorial, minus it over h bar to the power n. Then here we get sum over I, c I ai to the power n, ii, acting on a, and tensor product xx to the power n, psi 0 x. Yeah, then we take the summation over I. Did I make another mistake here? Sorry. Yeah, I confused this with the projector. So this is just J, right? Because it's just the state. Let me also substitute the summation over I with summation over J, since we also have the imaginary I here. M, J, A. Okay, this has to be correct. Okay, then we can take the sum over J first. So it will be sum over J, Cj, Ja, and then all other coefficients we put in the second part of the tensor product. So here we have sum over n, 1 over n factorial, minus it over h to the power n, aj to the power n goes here, xx to the power n, all of this acting on psi 0x. And what is this here? So this is what we have acting on psi 0x is just another exponential. So we can compactly write it as sum over j, cj, ja, tensor product e to the power minus it over h, a, j, xx, acting on psi 0x. Okay, so what does this mean? This means that we started with just the tensor product of the states on the systems A and X. And what we arrived to after evolving under this Hamiltonian, interaction Hamiltonian for the time t, is we arrived to the sum of the tensor products. So essentially in an entangled state between the systems A and X, where the state of the system X of the particle is correlated with the state of the system of the system A via this coefficients AJ. Okay. So now the next step is to understand. So we have this exponential acting on the wave function of psi 0x, and the next step is understanding how exactly this action turns out to be. And for this, we have to make a short interlude and look at the following operator, which is called the modular momentum operator. So the operator looks as follows. We can take just an example of exponential of minus IL x, where x is the operator, over h bar. And I claim that it acts on the wave function in the following way. In the position representation, it takes the wave function psi of x to psi of x e to the power minus ILx over h, where x is now just the value of the position, not an operator. So first we'll show this, and then we will show how it acts on the wave function in the momentum representation. Okay, so to prove this, we just have to act with this operator on the wave function psi, and then take the position representation. Okay, what we do again is we again write it out in terms of series. Factorial x to the power n psi. Okay, so we can take the sum out and only leave the x to the power n caged between the brackets of x to the power n psi. What we know is that x acts on x, it just returns the position x, because the position basis x is the eigenbasis of the position operator. Which means that if we look at the conjugates, then we arrive to this. Which means that we can just act with this bra on, so we can just act with this x to the power n on the bra, so on the left, and we arrive to, and we do it n times, right? So what we arrive to would be just x to the power n, where x is just the position value. Here we have x psi, which is the psi of x. And here what we have is exactly the exponential. So we arrive to psi of x e to the power minus ILX over h bar. Okay, so now we know how this modular momentum operator acts on the wave function in the position representation. Now, how does it act on the wave function in the momentum representation? So psi bar of p. So here we use the following trick. So we have our operator that we want to investigate, and then we know how it acts for the position representation. But we also know that the momentum representation, psi bar of p, is connected to the position representation via Fourier transform, which means that in order to find how this operator is represented in terms of the momentum wave function, we just have to take how it acts on the result of its action on the position representation, which is this one here, and perform a Fourier transform. And then we will arrive to the correct answer. Okay, so let us do it. So first, what we essentially need to do is to apply Fourier transform to the function psi of x e to the power minus Lx over h bar. So let us just do it. So this is our function. Now we add a Fourier transform. X. And we can put the two exponentials together. We have psi of x e to the power minus ix over h p plus l dx. Okay, what is this? This is exactly psi bar of p plus l. Okay, so what we found out then is that our operator e to the power minus l x over h acts on the position representation in the following way. It just acts on the momentum representation in the following way. It shifts the momentum by L. So in the lecture, you've seen the similar operator, but for shifting the position representation. Now this operator shifts the momentum. Okay, and then let us finish this interlude, and let us get back to what we got before. So to remind you, we had our unitary evolution, u of t, acting on the initial state. And what we got was this. Minus it over h, I x, acting on psi 0 of x. And now we know how this operator here, which is essentially the modular momentum operator, would act on the wave function psi 0. So if we take the wave function psi 0 in the momentum representation, then it would take so for example, let us just write psi 0 x as just psi 0 of p p dp. Then it would take each psi 0 of p and just shift it to psi 0 of p plus tai, because in this exponential, instead of L that we had above, we just have tai. So yeah, so in the momentum basis. What does that mean? It means that, for example, if we start with the, let us suppose that we start with the psi 0, which is just a pure momentum state. And if we start with this psi 0, which is a pure momentum state, then for each value of ai, after this evolution, it would shift the momentum differently. And every shifted momentum would correspond to the different state ai of the system of interest A, which we're trying to observe. And let us look at the concrete example, which are the Gaussians. Suppose that we start with our state psi 0 tilde of ax, which is the following. So the state of the system A is alpha 0 plus beta 1. Tensor product, the system X is initially in psi 0 x, which is a Gaussian state, which satisfies that its peak is at 0 at the t equals 0. Its spread is sigma squared, and the initial momentum is hk0. So essentially, at the time t0, for the psi 0, yeah, we start here. We start of x, and then for momentum representation, as we remember, the Gaussian for in the momentum representation is also a Gaussian. So here it's just around hk0. Initially. Okay, and then what we're trying to measure is the observable MA, which here we take as gamma ZA, where Z is just the Z operator acting on system A. So we can write it out as gamma 0, 0A minus gamma 1, 1A. And then we're looking at the Hamiltonian, which is H, MA, tensor product, XX. And coming back to our notation before, so maybe I'll write it with a different pen. So alpha and beta are C1 and C2, and gamma and minus gamma are A1 and A2. And given this, we can write down the final state. So the final state would be U of t acting on our psi 0 tilde ax would be alpha 0a, so the first component of the superposition on the system A. Tensor product, it would be coupled to the following: minus it over h gamma xx psi 0x plus the second component, beta 1a, tensor product e to the power plus it over h gamma xx, because the second coefficient, a2, was minus gamma. That's why the exponential changed the sign. The argument of the exponential changed the sign. Yeah, acting on psi 0 of x. And how can we imagine this graphically? Well, what happens to the Gaussian? So if we just look at the peak of the Gaussian, which started at hk0, just let us label just at p0, then essentially the first coupling here just shifts the peak of the Gaussian by gamma t. So kind of as for Gaussian peaks, we can kind of see this as coupling the zero state of the system A to the Gaussian states, to the Gaussian, which would be P0 plus gamma t, because this modular momentum operator here would just shift the peak of the Gaussian by gamma t. And the second one, what happens with the second one? Well, it also shifts, but in a different direction. So it kind of goes back. So essentially what we get for the beta 1, it's coupled to the P0 minus gamma t. So essentially, if we look at the graphical representation, so imagine that we're looking at the position, momentum representation, and we start with the Gaussian, which peak is at hk0. Then this is at time t0. Then what happens at time t? At time t, this one Gaussian peak in the superposition becomes 2. So this one is coupled to the 0, and this one is coupled to the 1, given that gamma is positive. And this one is peaked around hk0 plus gamma t, and this one is peaked around hk0 minus gamma t. And then we can just measure either the position, so the momentum which is bigger than hk0 or the momentum which is smaller than hk0, and that would correspond to measuring 0 or 1 of states of the system A correspondingly. You can also think about it as if we don't usually have in the lab any access to the state of the qubit. It's not like we can look ourselves on the state of the qubit and decide if it's 0 or 1. But usually what we do is we take some device with the like a sufficiently big device, which allows us to measure whether it's 0 or 1. And the device, what happens essentially is the device couples and interacts with a spin for a particular amount of time. And then, for example, it can have a certain pointer, which would then point to the left or to the right. And these two states just can be seen as these two pointers. On the device. Okay, so I essentially almost did the whole exercise except for the last part, which is to repeat this for a 2D Gaussian, where the Hamiltonian just to another tensor product is added to the Hamiltonian with the y direction. But this is quite straightforward, and it's almost the derivation is essentially the same. Okay, so now let us come to the second exercise. So the second exercise tackles a topic in quantum information, which is called non-local games. And we will be looking at the particular, just non-local games. And we will be looking at the particular instance of such a game, which is called the GHZ game. So in a previous exercise class, you've seen, in the previous exercise sheet, you've seen that two parties, Alice and Bob, sharing entanglement, can do very interesting things. For example, they can teleport a quantum state from one lab to another. So essentially just pass on the information about the quantum state from one lab to another. So the entanglement in that sense was a useful resource for these two parties, Alice and Bob. So this, the non-local games is just another way to show why entanglement is indeed a useful resource. It's another setting. And also, this is a way to study quantum correlations between parties. And these are the certain games which go the following way. So imagine that you have a certain number of parties which share an entangled state. And in our setting here, in the JZ game, we have three such parties, which we call Alice, Bob, and Charlie. And in this game, there is also a referee who governs the game. And what the referee does, the referee sends Alice, Bob, and Charlie each their own bit, RST. So RST can take values 0 and 1. And the parties which are involved in this game, they're assumed to be, like, for example, in places which are very far away and they don't have any communication they don't have any ways to communicate to each other, so they have to kind of make decisions on their own. So essentially, a referee just sends them each one of them 0 or 1, and then each one of the parties has to produce a certain number as a response, which would also be a bit 0 or 1. Then referee collects these three answers, A, B, and C, given by Alice, Bob, and Charlie, and then based on some predicate, the referee evaluates some predicate of RS, A, B, C, and decides, and this will determine whether they win or not. So essentially, again, referee just sends this 3 bits. Alice, Bob, and Charlie has to produce another 3 bits. And then based on these 3 bits that they produce independently, not without any classical communication to each other, it is determined whether they win or they lose. And in the GSZ game, the first 3 bits that the referee sends to the parties are S and T. They are chosen from this string set. So 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. And so referee chooses uniformly from this set. And then the winning conditions are if the mod 2 sum of the answers that Alice, Bob, and Charlie produce, A plus B plus C, equals to R or S or T, which in other words just corresponds to the following table. So suppose that we have here the incoming string, RST, and here we have A plus B plus C, mod 2. So if the incoming string is 0, 0, 0, Alice, Bob, and Charlie win if A plus B plus C equals 0. If the incoming string is 0, 1, 1, they win if the sum modus 2 is 1. If the incoming string is 1, 0, 1, they win if it's 1. And if the incoming string is 1, 1, 0, then they win if it's 1. And you might ask why do we need an entangled state here? Well, so first, if we consider any deterministic strategy that Alice and Bob and Charlie can have, by deterministic strategy, I mean that they have each one of them has their own strategy of what to answer if the referee sends 0 and what to answer if the referee sends 1. So if we take any such deterministic strategy, they only win with the particular probability. So they don't win all the time, but they win only 3/4 of the time. However, if we look at the case where Alice, Bob, and Charlie share an entangled state, then they can come up with the kind of a quantum strategy, each one of them in their own lab, without classically communicating, such that they will be able to win in 100% of the times. So they would be able to win all the time. And that highlights how quantum correlations in this case can be more powerful than any classical correlations that they can come up with without an entangled state. Okay, and so first, let us consider a deterministic strategy that they might have, and let us show that there is no deterministic strategy which would allow them to win all the time. Okay, so suppose that for Alice, she has a deterministic strategy to output A0. So if she sends 0, then she outputs A0. If she sent 1, she outputs A1. Same for Bob and Charlie. B0, B1, and Charlie C0, C1. Then suppose that there exists a strategy which allows to win all the time. Then we can write out, based on this winning table, just 4 equations. So if they all got 0, then the sum of their outputs, mod 2, has to be 0. Then if here output 0, here 1, and here 1, it has to be 1. If here is 1, 0, 1 has to be 1 again. And finally, 1, 1, 0 also has to be 1. Okay. Let us sum all of these equations. What we get is we get 2a0 plus 2b0 plus 2c0 plus 2b1 plus 2 a1 plus 2c1 equals 1. Okay, so 2a1, 2a0, 2b0, 2c0, and so on. So they're all, since this is all summation modulus 2, then they will all give you 0, and then we arrive to 0 equals 1. Okay, this is a contradiction, which means that there doesn't exist a deterministic strategy which allows to win all the time. So this is already not good. One can easily see that the best strategy that they come up with is if they just output 1 all the time, all of them, no matter what they get. And 1 all the time. In that case, if they all output 1 all the time, then the sum of their answers modulus 2 would be 1 all the time. And essentially, they would just win in all of these 3 cases, which means that this is a win with probability 3/4. Another thing one can show is, you might ask, why do we jump directly from deterministic strategy to some quantum strategy? What about probabilistic strategies? If when Alice outputs a0, when Alice outputs 0 with some probability, and 1 with some probability based on her, on which bit she gets from referee. Well, it can be also shown, which we will not prove here, that probabilistic strategies don't do better than 3/4. Which makes sense because the probabilistic strategy in the end is just the converse combination of the deterministic strategies, and if the best deterministic strategy is has only 75% success rate, then the probabilistic strategy will not do better. But now let us come to the quantum strategy. Which will show it wins all the time. And here we start with supposing that Alice, Bob, and Charlie share a following entangled state. Which I will write just here. Psi on systems A, B, C. So yeah, so we label the systems which Alice, Bob, and Charlie have access to as A, B, C. 1/2 0, 0, 0, ABC. Here we write 0, 0, 0, ABC. This corresponds to 0 on A, 0 on B, 0 on C. Tensor product. Just for convention, I'll be writing it as just 0, 0, 0. Minus 1/2 0, 1, 1 ABC. here's the same. It's 0 on A, 1 on B, 1 on C, minus 1/2, 1, 0, 1, ABC, minus 1/2, 1, 1, 0, ABC. And I propose the following strategy. So if and this is a strategy for all three of them, Alice, Bob, and Charlie. So if they get the question, if question Q equals 1, so if they get the question 1, the bit 1, then they perform a Hadamard gate on their qubit. So just to remind you, the Hadamard gate looks the following way. And it transforms 0 to 1 square root of 2, 0 plus 1, and 1 to 1 square over square root of 2, 0 minus 1. And if question Q equals 0, then they don't do anything. Okay, now let us show why this strategy allows them to win all the time. And for that, we will need to consider cases. And here only consider 2 cases. All other cases are similar to the second one that I'll consider. So now we will be considering cases of which strings were chosen by the referee. So which bits the referee had chosen to send them. So first, he could have sent them all 0. So the initial string of the bits of which the referee sent them individually could be 0, 0, 0, 0. Then, according to the strategy that we proposed above, none of them does anything. So then the state that they end up with would be just the initial state that we've written above. Sorry, of course, yeah, I forgot a very important thing that we have to do, which is, yeah, they perform these operations, but what they still need to output some answer in the end, right? So in the end, they each measure their qubit in the computational basis, 0, 1. So again, the strategy is that if they get 1, they perform a Hadamard on their qubit. If they get 0, they don't do anything. And then they measure their qubit in 0, 1 basis. Okay. So back to our cases. So the first case is when none of them do anything. And now they have to measure in computational basis, 0, 1. Each one of them has to do so. And because it's a computational basis and all our states are written out in a computational basis, we can predict which kind of answers they can get. And essentially, the only collections, since their answers are correlated with each other in the particular way that this entangled state tells us, they can only get a certain combinations of answers together. So the first combination is ABC that they all measure in the computational basis, and they all get outcome 0, 0, 0. Then the second one is 0, 1, 1. The third one is 1, 0, 1. And the fourth one is 1, 1, 0. What is similar about all these answers, all these combinations of answers that they output? Well, is this one similarity is that for all these answers, the sum of A plus B plus C modulus 2 is 0, which is exactly what they need for winning. So for this case, we won. Now let us consider the second case, where RST that the referee chooses is 0, 1, 1. Okay, in this case, Bob and Charlie, since they get the bit 1 from the referee, have to employ a Hadamard gate, which means that the resulting state, psi tilde on ABC, would look as follows. Nothing happens on system A, Hadamard on system B, Hadamard on system C, and our state, psi ABC. Okay, and here to write out how the state will look like, maybe first I'll just, for pedagogical reasons, I'll write out the state here again. So here we have 0, 0, 0, minus 0, 1, 1, minus 1, 0, 1, minus 1, 1, 0. Here I use the trick. I know how the Hadamard gate acts on the 0 and 1. So 0, it transforms to 1 over square root of 2, 0 plus 1. 1 transforms to 1 over square root of 2, 0 minus 1. Right, and then I will not write it in terms of the matrix, since this looks a bit scary to me. But what I can do is just like I can take, for example, the state 0 here of the system B, and instead of it, just write out 1 over square root of 2, 0 plus 1, because this is exactly how the Hadamard acts. Okay, so now let us start acting. So identity Hadamard acting on 0, 0, 0. So the 0 on A stays. Nothing happens. Then what happens on B? 0 goes to 0 plus 1. Okay, what happens on C? 0 also goes to 0 plus 1. Okay, the first term is done. Then the second one, 0, 1, 1. On A, nothing happens. On B, 1 is transformed into 0 minus 1. On C, 1 is transformed into 0 minus 1. Okay. Now the third state, which is 1, 0, 1. 1 stays. 0 is transformed into 0 plus 1. And 1 is transformed into 0 minus 1. Okay. And finally, the last term in the sum, 1, 1, 0. 1 on A stays. Then 1 on B is transformed in 0 minus 1. And 0 on C is transformed to 0 plus 1. Okay, we've done our evolution. Now we only have to open the brackets, and you can calculate it yourself, but what you will get in the end would be the following: 1/2 0, 0, 1 ABC plus 0, 1, 0 minus 1, 0, 0 plus 1, 1, 1. Okay, and again, after Bob and Charlie perform their Hadamards, all three of them, Alice, Bob, and Charlie, they measure their state, their qubit that they have access to in the computational basis. And again, there is only a certain combinations that of A, B, C, of the answers A, B, C, that they can get in the end. So the first one is 0, 0, 1. The second one is 0, 1, 0. Third one is 1, 0, 0. And fourth one is 1, 1, 1. What is similar about all these answers is that A plus B plus C modulus 2 would be equal 1. Again, win. And the rest of the cases for which RST, the initial string chosen by referee, is 1, 0, 1 or 1, 1, 0, you can see that they're symmetric with respect to this one, because the initial state is like up to some signs. It's symmetric with respect to A, B, and C, systems A, B, and C. And so in the end, up to some minus signs, the result of the action of the Hadamards in two other cases would be essentially similar to this case. And this will guarantee the win again. So essentially what this exercise shows us is that entanglement can be also useful resource for this type of non-local games. And it can create correlations, which would be in this sense more powerful than the classical correlations. And they would allow the parties to win in more cases than they would win if they could only use deterministic or even probabilistic strategies. Okay, I think yeah, this is all I had for today. Are there any questions? Okay. Yeah, I have to apologize if you ever find in the exercise sheet some typos in terms of signs or coefficients or superscripts or subscripts, because sometimes I make these mistakes while typing. So let me know if you find any. You can always send me questions by an email. You can also join the question and answer session on Tuesdays, which is now unfortunately only online because of the number of cases rising in Zurich. So this is it for today. Thank you. Have a nice weekend.